We are going to be talking today about an introduction to amplifier circuits. So let's say that I have a waveform. As a function of time. Something like this, and I want a larger version of that waveform. Something like this. How can I achieve this? There are really two ways I can do it, okay? So the first way, and the one that we're going to focus on in this class, is the use of an amplifier. But another way to achieve this would be the use of a transformer. Okay? And just for the sake of argument, this waveform could be a voltage, a current, or power. And this waveform could also be a voltage, current, or power. There are amplifiers and transformers for all of these quantities. Okay. So let's talk about some of the fundamental differences between amplifiers and transformers, or how we can increase the level of a signal. Okay. So probably the largest difference between an amplifier and a transformer is that an amplifier is an active device or circuit. Okay. So an active device means that it requires external power. Meaning we have to supply some amount of energy in order to boost the level of our signal. In contrast, transformers are passive devices. Meaning that they do not require any external power. So a transformer is really a very complicated, but in some ways simple circuit element like resistors, capacitors, and inductors that behave that particular way without the application of any external power. So because we can get, or because for an amplifier, we have to supply some form of external power, this means that the output power of our amplifier does not have to equal the input power. A better way to state this would actually be that the output power of an amplifier can be greater than the input power of the signal that you're putting in, because you can use external power to supplement it and drive it. Right? In a transformer, speaking specifically about an ideal transformer, the output power will always be less than or equal to the input power. So in an ideal case, what you get out of a transformer is exactly what you put in, but in any practical case, it's going to be less than what you put in because of the resistance of the wires, the energy it takes to magnetize the transformer's core, and a lot of other things that are well beyond the scope of this class, but but that you'll learn about in other classes. Right? So these are two different ways, and in circuits 2, we start off by talking about amplifiers, and in circuit 3, we start off by talking about transformers. Okay. So what does an amplifier do? Its entire job is to make a signal larger, or to scale a signal by some amount. So an amplifier, as a simple definition here, is an electrical device or circuit which increases the magnitude of the signal applied at its input. So we're not going to worry too much about the specifics of things here, and I'll show you guys why in just a moment. But for the most part, we can think of an amplifier as just a large black box network. I am not, just for those of you that are paying attention, saying that this is a linear black box network. So on the left-hand side, we have some input signal X of t. On the right-hand side, we have our output signal Y of t. And generally speaking, Y of t will be A, our gain, or a scaling factor, multiplied by X of t, our input signal. I'm just going to put a note here. This A represents the gain. Another way to think about the gain of the amplifier is it's the transfer function of the amplifier. And so what I mean by that is it acts on the input signal to generate the output signal. So it's simply the ratio of the output divided by the input. Okay. Now, there are lots and lots of different ways to classify amplifiers. Okay. In this class, we are going to classify amplifiers by their input and output signals. Okay, so if we were dealing with transistor amplifiers and stuff like that, you get like class A, class B, class AB, all that kind of stuff. That's well beyond what we're going to talk about here. In this class, we're going to talk about voltage amplifiers and current amplifiers and power amplifiers and things like that. Okay, so I'm going to make a real simple table here. Input, output, and amplifier type. So if we apply a voltage signal at the input and we get a voltage signal at the output, guess what? We have a voltage amplifier. Makes sense, right? Similarly, if we apply a current at the input, measure a current at the output, we have, I put too many R's there, excuse me, a current amplifier. If we apply a voltage at the input and measure a current at the output, we have a transconductance amplifier. The most common transconductance amplifier is simply a transistor. That's exactly what they do. They convert a voltage at the input into the current at the output. if we apply a current at the input and get a voltage at the output, we have a trans resistance, or more commonly called trans impedance amplifier. And then finally, we put power at the input, measure power at the output. We have a power amplifier. So once again, we're coming to things where we're going to learn about all of these as you progress through your electrical engineering career. But for the most part in this class, we're going to focus on the simplest case of voltage amplifiers, voltage at the input and voltage at the output. Okay. So I want us to consider a simple voltage amplifier circuit. I'm going to go to the next page so I can draw a pretty picture here. So I'm going to start with my amplifier here in the middle of the page. Here is my input voltage. Let's assume it's time varying. It doesn't have to be, but we'll just assume that it is. And here is my output voltage, right? This middle section is my amplifier. On the left-hand side, we are going to have our source. So this is providing the signal that we are trying to amplify. And for the sake of argument, let's say that our signal generator has some internal resistance. So we're going to represent this like a practical voltage source. Like so. So over here, we are on our source or signal side, and I'm just going to put a red line here to break up the stage. And on the output side, we are going to have some load. For simplicity's sake, we're going to say that this is a resistive load, but that does not have to be the case. And I'm going to draw some lines here to separate this stage. Okay. So these are the three different parts of a voltage amplifier circuit. Okay. We have an input voltage source generating some signal that gets applied to the input terminals of our amplifier. Our amplifier then amplifies that signal and applies it at the output, and then we measure some voltage drop across our load to see the effects of the amplification. Okay. So in the ideal case, what we should see is that the voltage drop across our load is a scaled version of the voltage drop being, or the voltage being supplied by our source or our signal generator, right? So in an ideal case, our load voltage VL of T will simply be the gain of the amplifier system times our signal voltage, Vs. we don't really have access to ideal amplifiers. We have access to practical amplifiers that are in some way, shape, or form going to put their own stamp on this transfer of information across our amplifier. Okay. So what we are going to do is we are going to develop here just by using Thevenin and Norton equivalent circuits, or really Thevenin equivalent circuits and a little bit of knowledge, a practical amplifier model that will work for effectively any voltage amplifier, regardless of how complex it is. Okay. So before we do that, I want to show you why we need to use a simplified practical amplifier model. So I'm going to pull up a data sheet for Texas Instruments MU-A 741 op amp. Scroll down a few pages. On a trucking, here we go. Let me zoom out a little bit. For those of you that took me for circuits 1, you've already seen this. This is a simplified representation of the internal structure of an operational amplifier. Okay. The MU-A 741 op amp isn't some specialized piece of equipment. It is pretty much the most basic op amp that you can buy off the shelf. Okay. This is a general purpose amplifier. It has been in use for 60 plus years at this point. This is as quote unquote simple as it gets, and it is wildly convoluted with our current level of circuits knowledge. Okay. For those of you that want to suffer through taking my integrated circuits class and all that kind of stuff, we literally design one of these things from the wafer up. Okay. That's a problem for roughly 2 years from now. Okay. So for right now, we just need to recognize that, well, there's some input terminals and there's some output terminals and there's some amplification that goes on. So how can we make this look like something that we can do something with? Okay. So let's go back to this little representation here. So might seem kind of weird. Well, let's disconnect the source. Okay, so just imagine that the source was disconnected and we are looking in through those input terminals, trying to find a Thevenin equivalent. What do you think we would see? So do we have anything exciting this system? No. So that means we're not going to see a voltage or anything like that. So if we're dealing with a Thevenin equivalent circuit and the voltage is 0, what's that leave? A resistance. So we are going to have some input resistance that is characteristic of everything to the right of these source terminals. Okay, so that's the first part of our practical model. So I'm going to draw that here in the center. So here's our input resistance. Here is our input terminals of our amplifier. And then over here, these are our output terminals. So let's scroll back down here and figure out what's connected there. So if we were to disconnect our load resistance and look in, what Thevenin equivalent circuit would we see? Are we going to have a voltage drop across these terminals? Probably, because there's a signal voltage being applied to our system. And then we're going to also see some resistance because it's a Thevenin equivalent circuit. We're going to see a voltage source in series with a resistance. Okay. So we're going to call that resistance our output resistance. R out. And this is going to be a little bit weird here. Okay. Instead of putting in a independent voltage source, I'm putting in a dependent voltage source. So let me explain why. We are expecting that the output voltage seen at the terminals, the output terminals of our amplifier is a scaled version of whatever we have at the input. So we're going to say that the voltage here depends on the applied voltage over here. So I'm going to call this AVOL, and we'll talk about that in a moment, times Vn. And then here is our output voltage as a function of time. And then let's connect the other pieces. I'm genuinely concerned that the Zoom might have picked up my stomach growling. I am in dire need of a sandwich. Sorry, this should be VL of T. Actually, let me move this RL to this side just so I can move this voltage a little closer. Everything in the middle here is what we're going to call the practical voltage amplifier model. Okay. Well, technically, we're not done here, and I want to explain what I mean by that. Okay. So the purpose of this model is to represent any amplifier circuit, or excuse me, any voltage amplifier circuit by its input resistance R in, its output resistance R out, and its open loop voltage gain. So AV means, so A is gain. The subscript V lets us know that it's a voltage gain. And the subscript OL here lets us know that it is an open loop voltage gain, so that we do not have any type of feedback network applied to the circuit. And we'll talk about that in a lot more detail in this class, as well as your transistor amplifier classes and all that kind of stuff. Now, there is a very small problem with this circuit. We can't use it for op-amps. Let me explain why we can't use it for op-amps. How many input signals can an op-amp take? Let's look. There's an input plus, and there's an input minus, right? There's only one output. So an operational amplifier is what's called a differential amplifier, because it actually amplifies the difference between these two inputs, or at least that's arguably what it's supposed to do, but we use it for lots of other things and practically never that. We use that for comparators. We'll talk about those on Monday, right? So we have a double-ended input because there are two places that we can apply input signals, and we can absolutely apply signals to both of them. And we have a single-ended output. Well, in this model, we only have space for a single-ended input. So we're going to have to modify this really slightly, okay? So our op-amp model, which is just a modification of this thing, is going to look like this. So this terminal, I'm going to label with V plus. This is for our non-inverting input terminal of our op amp. Here we have our input resistance. And this terminal is V minus for our inverting input terminal of our op amp. So we see that our input resistance is what we measure looking in between our two different input terminals. And then on the output side, we're effectively going to have the exact same thing as we have the output side of our single-ended amplifier model. We are going to have a dependent voltage source having a value of AVOL times VD. This VD is for a differential voltage. And the differential voltage is simply the voltage difference measured between our non-inverting input terminal and our inverting input terminal. And I want to be very clear here. This is always the polarity. Positive polarity of VD is associated with the non-inverting input terminal. Negative polarity of VD is associated with the inverting input terminal. Up here is our output resistance. And then just for the sake of simplicity, I'm going to put common rail here down on the bottom. That is our ground. And between this output terminal and ground is where we measure our output. So this construct right here is the practical amplifier model for an op amp. And it's where we're going to start our analysis, and we're going to work towards what we were using in circuits 1. Okay. So this thing right here represents the triangular schematic diagram model that we're used to, where this terminal is V plus, this terminal is V minus, and this terminal is V out. So effectively, everywhere in our schematics that we see this, we can replace it with this, and we can do real circuit analysis without saying, oh, there's special rules and all that kind of stuff. We'll figure out why those special rules are there, the ones that we used in circuit 1 in a little bit. Everybody okay? I see you can, yes.
So that's just the stuff that's in the class.
Mm-hmm. Yes, absolutely right. So for, okay, so what I'm going to do now is we're going to work an example problem, and we're going to find out pretty quickly that there's a pretty big flaw in this model. It's just not. Now, I know you're like, son of a bitch, this guy is just making us write down all of these weird things. Okay, there's nothing wrong with this model. You can find all 3 of these pieces of information in the data sheet of the amplifier. There is a limitation in the model because nowhere does it include the fact that we have external power. That's the limitation. Okay, so this absolutely works, but we have to be careful when we apply it because we're using external power, and that is going to have an effect on what the size of the output signal can be. Other than that, we're good to go with this for all intents and purposes. Okay, so I'm going to go to another page just because I'm not 100% sure there's enough room here. So what we're going to do is we're going to analyze the following circuit. Okay. So let's say that I have an op amp like so. I am going to connect a 1-volt source to the non-inverting input terminal. I'm going to ground the inverting input terminal. I'm going to specifically specify here that I am applying 10 volts on the positive power supply terminal and negative 10 volts on the negative power supply terminal. And I'm going to measure my output voltage here with respect to ground, like so. And just for the sake of argument, let's specify our open loop voltage gain. So let's say that it's 100,000 volts per volt, which you may think, gosh, that is huge. That's actually pretty shitty for a commercial op-amp. It's not uncommon for them to be several hundred thousands, if not millions, of voltage gain. Okay. Let's say that our input resistance is 1 mega ohm. So an input resistance of 1 mega ohm is pretty standard for operational amplifiers that are based on bipolar junction transistor technologies, or amplifiers, for op-amps that are based on MOSFET, so metal oxide semiconductor field effect transistor technology. This number is usually about 1 million times larger than 1 million ohms. So it's in the tera ohm range. Okay. Our output resistance here, let's say, is 25 ohms, which would actually be kind of bad for an op-amp. Typically speaking, this would be on the higher end of output resistances we would see. There are a lot of commercial op-amps where their output resistance is on the order of milliohms. Okay. So anything higher than 100 ohms is usually a pretty bad design for an op-amp. So the first thing that we're going to do here, our goal is just to figure out what this output voltage is going to be. Okay. We don't have negative feedback or anything like that, so we can't apply any of those rules and all that kind of stuff that we learned in circuits 1. So we're going to have to replace the op-amp in the middle here with our practical op-amp model and just see what falls out. Okay. So let's talk about how we're going to draw this. This is important. You're going to have to do it multiple times. All right. So I'm going to start with the op-amp model by itself. So here is Rn. This is V plus. This is V minus. Over on this side, I have my dependent voltage source. I'm just going to leave this as AVOL times VD for right now. Let me make sure that you guys are aware that this is VD. Here I have my output resistance, R out. And for now, let's leave the output open circuited. Talk about what happens if we put a load resistor there in a moment. This is the V out that we're looking for. Okay. So I have everything to the right of where my hand is right now drawn. Now I need to figure out how to make my external connection. So my inverting input terminal is connected directly to ground. So I'm literally just going to draw a wire from my inverting input terminal to ground. Call that a day. And then over on my non-inverting input terminal, I have a 1 volt source between the non-inverting input terminal and ground. So I'm going to place a 1 volt source between my non-inverting input terminal and ground out here. So let's start with a straightforward question. Does this equivalent circuit match what we have up above for our schematic diagram? All of our external connections are in the same places, and we have just replaced this triangular op-amp model with the practical op-amp model that we developed. Okay, so these two things are essentially equivalent. So let's analyze this. Right, this isn't going to take a whole heck of a lot of work because I'm giving you guys a softball thing for right now. What's VD? Our differential voltage. It's 1 volt. Absolutely right. AVOL times VD would then be 100,000 volts, which means there's 100,000 volts between here and here. Since we have an open circuit on our output, the out is then 100,000 volts. Does that make sense? From a circuit analysis perspective, sure. From an actual practical circuit perspective, good Lord, no, right? I can't plug a power supply into one of these outlets here, wire up a circuit like this, which we could easily do. The only hard part would be finding a 1 volt source. We could just up it up to 1.5 and use a AA battery. And there's no practical way that I would expect 100,000 volts at the output of that circuit. We would either be creating free energy or I would accidentally kill all of you. There would no way that could be safe. Okay. So the problem with this model is that it's neglecting the fact that the amplification occurs due to the application of outside power. Okay. For an op-amp circuit, we should never expect the output voltage to be more positive than the positive power supply voltage or more negative than the negative power supply voltage. This phenomenon is called saturation distortion. Okay. So effectively, in an open loop configuration like this, what we are going to see is that the output signal saturates to the positive supply voltage or the negative supply voltage for pretty much any signal that we can put on this thing. There are some cases where we're going to have amplification, and we'll talk about that here in just a moment. Okay. So let me write some stuff down here. V out does not equal 100,000 volts. That would be wildly dangerous. Now, for saturation distortion, you can simply say that in a real op-amp, the output voltage cannot exceed the power supply voltages. And I'm going to draw, or I'm going to give you guys a little bit of a piecewise function here. Okay. So we're going to say that V out will be equal to VCC plus our positive power supply voltage when AVOL times V plus minus V minus is greater than or equal to VCC plus. So effectively, I'm saying if this voltage is ever greater than VCC plus, the output is simply VCC plus. Can't be more positive than that. Okay. On the other side, we're going to have an output voltage of VCC minus, which is our negative supply voltage. This will occur when AVOL times V plus minus V minus is equal to or more negative than VCC minus. So if we were to put a negative 1 volt source on the input of this thing, we would expect our output to saturate to the negative supply voltage. Okay. But there's something in the middle as well. Okay. So for this particular circuit where we have the output open circuited, we would see that our output will be AVOL times our differential voltage when AVOL times our differential voltage is between VCC minus and VCC plus. So we effectively have 3 different points of operation. Okay. We have positive saturation on this side. Negative saturation on this side. And then in the middle, we have a linear region of operation. So I'll talk very briefly. This isn't wildly important for this class, but the concept of saturation is going to show up a whole heck of a lot in the field of electrical engineering. So I want to talk to you about where that term comes from so that when you see it here and in later classes and all that kind of stuff, it kind of makes sense. So what saturation means in electrical engineering is that a change in the output signal does not generate a corresponding change. Which means a change in the input signal does not generate a corresponding change in the output. So in this case, it doesn't matter how much larger our differential voltage gets, our output stays constant. So our output is said to be saturated at the positive supply level. Similarly here, it doesn't matter how much more negative my differential voltage gets, any change in it will only cause the output to stay at negative saturation, right? So that's what saturation is. Completely different to saturation is the linear region of operation, where a change in the input causes a corresponding change in the output. So in this region, as long as this whole quantity stays left between VCC minus and VCC plus, we have linear amplification. So for very, very small input signals on the order of microvolts for some op amps, we can get linear amplification. So now let's talk very briefly about figuring out what the linear range of an amplifier is. So the linear range of an amplifier is effectively the size of the input signals that can actually undergo linear amplification. And this depends on the power supply voltages, because the power supply voltages are what limits what our possible output voltages can be. Oops, sorry. So our linear range mathematically is simply VCC minus over our open loop voltage gain will be less than, in this case, our differential voltage, because that's the true input here, will be less than VCC plus over our open loop voltage gain. So if we were to throw numbers into this thing, we would see that for the particular amplifier that we are looking at, where VCC minus was negative 10 volts. AVOL 100,000 is the same thing as 10 to the 5 volts per volt, will be less than VD, will be less than positive 10 volts over that same 10 to the 5 volts per volt. This means that our linear range is effectively negative 100 microvolts to positive 100 microvolts. So any input signal or any differential voltage that is outside of that range will cause this particular amplifier to enter into saturation. All right, so that's where we're going to stop for today with regards to electric, okay? What we are going to do on Monday's class meeting is explore how this extremely small linear range can actually be used for some practical purpose, right? Because it seems right now that if our amplifier can only amplify signals that fall within this very tiny window, this amplifier probably isn't particularly useful, but we can literally go buy them from Mauser. I would be willing to bet there's hundreds of millions of them that have been sold, okay? So we're going to talk about how we make this device, which seems pretty flawed, work for us in open loop configurations, positive feedback configurations, and negative feedback configurations. Okay, so that's what we're going to be talking about. All right, so I am done with the lecture part. I heard a couple of people talking about homework related stuff. I would be happy to answer anything, entertain any questions you may have about that. If you don't have any questions, see you on Monday. Yes, ma'am.
So, a page or two back, when you were doing the practical document,
Mm-hmm.
I'm a little confused about how to.
Okay, so you're confused because they're not connected to each other. Okay. How can I explain this? Because you're correct, that does seem weird. There's isolation effectively because there has to be. We're seeing two different things when we look at the two different ports, right? So when we look in through the input, we see the input equivalent circuit. When we look in through the output, we see the output equivalent circuit. And we know that those two equivalent circuits are coupled to each other because this is an amplifier. So we're expecting to see if we put something in here, we get a larger version of it here. So it's just making sense of what our expected behavior would be for this circuit. Now, there is actually physical isolation and all of that kind of stuff that is established by the input resistances of the various transistor stages and all of that kind of stuff as well. But that's well beyond the scope of this class. So I can completely understand why you might think this would be magic. I would argue understanding why we can say this horrifying big thing right here looks like this little thing right here is a bigger leap of faith. But I'm going to expect you to make them because it's well beyond the scope of what we're talking about here. I know that this is annoying, but it's kind of like how in Circuits 1, we get to use all of these little simplified models that are based on electromagnetic field theory without ever using electromagnetic field theory because it's too damn hard. So it's a similar thing here. All of this is based off of an incredibly detailed analysis of transistor amplifier models. And we are just reaping the benefits of the fact that it can simplify to something like this that we can analyze with our current level of circuits knowledge. The ground came from the fact that we are going to have a ground reference for our power supplies, right? So up here, we're effectively saying this entire bottom rail is ground. Now we are saying that our input resistance is at some floating potential above ground that depends on what voltage we apply at our non-inverting input terminal and our inverting input terminal. Since we have a differential input, this isn't forced to be zero like it is up here. I know that's not a great answer, but that's the only one I can give you.
Yeah.
So this Vs of t is measured. So this is the positive polarity terminal of Vs of t, and this is the negative polarity terminal of Vs of t, right? And we could just as easily say that this is ground, so that this is measured with respect to ground as well, because we know that this output is just a scaled version of the input. So it should have a same ground reference on either side of the representation. All we're doing is we're no longer forcing the negative polarity terminal here to be at ground so that we can have a differential input signal. So this is going to be the difference of whatever voltages we apply. This one could be zero. We're forcing this one to be zero with this one. It's all from the semantics of single-ended inputs versus double-ended inputs with ground as a common reference. Anything else? Homeworks, this stuff. I'm gonna level with you guys, okay? These first couple of lectures and this stuff, you're gonna be like, what the hell is happening? I promise it's going to get better in like 3-ish days, okay? It is a large leap of faith to say that huge, ugly transistor-based thing can be simplified down to this, but that's literally how they are analyzed in industry, because not everybody needs to know all of the background of how all of the transistors interconnect and all of that kind of good stuff. Okay, so, yes. Absolutely not. If you can do it in your calculator, that is perfectly fine. You could say solving in my calculator, and then that would be good, but it really doesn't matter. But that being said, if you're doing something that's an equation of, 6 equations, or excuse me, a system that's like 6 equations and 6 unknowns, I know for sure you couldn't do it in your calculator because your calculator can't do it. So, yeah, I mean, if you can do it in your calculator, I have no problem with that whatsoever. Yes. Yeah, so typically speaking, if you'll notice that right now it's 11:56, this class doesn't end until 12:15. I don't like talking for the full time, and you guys usually don't like listening to me talk for the full time either. I tend to wrap up 5, 10, 15 minutes early so that we can talk about things if we need to, and the other people can know about what they're doing. So yeah, and I also will have office hours as soon as I get them posted that start at 12:30, I believe, and end at 2. So that's effectively whenever this class ends to 2 p.m. I'm available for questions as well. Yes, ma'am.
Okay. So I understand.
Go for it.
I understand how it's a differential voltage when that bottom strip is not ground, and how the other one is connected to ground. Bottom strip is ground.
Okay.
So are you like just assuming two different?
So I mean, you can argue that this is the differential. It's just always the difference between this point and 0. This is just saying this one doesn't have to be 0. So this voltage right here is measured with respect to ground. This voltage right here is measured with respect to whatever potential this thing is at. That's the difference between these two circuits.
So I guess what I'm confused with, like, if V minus is not, why is the dependent source still connected?
Okay, Because we have isolation between the input side and the output side, right? So we have this circuit with a ground here, this circuit with a ground here. We're effectively breaking this ground to allow for the fact that this voltage here isn't ground, but this side is still grounded. Okay. And it's because, again, we're physically connecting this device to a power supply that has a ground reference that is our electrical grid and all of that kind of stuff. So the external power has some zero reference. Our output voltage is measured with respect to that purely because I said it is, right? No, and I mean that literally. If we were to wire up a circuit and we didn't put our load resistance between here and ground, the number would change, right? If I threw another resistor here and then said my output voltage is this thing, that might be different depending on what the value of that resistor is and all that kind of stuff. We're just establishing a simple baseline with ground as a common reference point because that's literally the job of ground, to be a common reference point. So this voltage is measured with respect to ground. This voltage is measured with respect to ground. Doesn't matter if this one's larger than ground or more negative than ground. Same thing here, but ground is serving as our common reference point because effectively we're just going to wind up doing a lot of nodal analysis when we analyze these things with feedback. Yeah. And yes, Gabriel.
You recommend us taking a calculator that can do plus class of the log
Three system. I would argue you're probably not going to have to do much system equation manipulations in this class. Three should be whatever calculator you have for engineering 221 will be good enough for this class for sure. Anything difficult is going to be on a take-home portion of the test. Yes.
Other than a signal flatlining, are there any bad things on like point saturation?
No. I mean, I say no, like if you were to put some huge voltage at the input or something like that, like you could burn out the op amp or something because you could have dielectric breakdown that would literally fry the internal circuitry. But from a performance perspective, there's nothing bad about saturating at the supply rails. It's just what the physical limitation of the system is. Yes.
Didn't need rewriting faults on board, are we allowed to like copy an interim thing based on word and just write them?
For sure, yes. Yes, absolutely. Yeah, don't waste 30 plus minutes of your time rewriting the stuff that I've already given you. Yes, Paige. This is, you're gonna have to PDF annotator. Yep, it's a horrifying mess. I have not deleted stuff off of that desktop thing in like probably 4 years at this point, and so just so many, like LT Spice randomly saves files there. Electric, which is a software program that I use to design amplifier circuits and all that kind of stuff, saves files there. So please ignore how horrifyingly ugly that desktop was. But it's called PDF annotator. I think it cost about $50 for 2 licenses. But it was way cheaper than whatever Adobe's product would be that would let me draw on PDFs. Yep, I found a PDF of engineering paper, and then I made 12 copies of it because my notes for a single class have never gone beyond 12 pages. So that's what I have. Yeah, but I mean, if you want to do the homework, like I don't mind if it's on white, like a white background or anything like that, just like it would be on normal white copy paper, but you're going to be uploading it as a PDF, which will put it in Pages for my grader's ease. So you want to make sure that it doesn't break in the middle of an equation or anything like that, which you should be able to see in like a print preview or anything. It's an ever flowing page. Yep, which is why I don't like it. Yes, Brent. I don't particularly have a problem with that because that's the way that I make my solutions for these out. So I can't say, well, I can do it, but you can't. That being said, you probably do at some point want to get in the habit of using your calculator for some of this stuff because you are going to be tested on it. where you can't just use MathCAD for everything. But I absolutely just use MathCAD for everything. So. Anything else? All right, I will see you guys on Monday.